In this part of the lecture, I will talk about thermal equilibrium. I will also discuss the zeroth, first, and third laws of thermodynamics. And I will talk about specific heat and heat capacity. Let's first talk about thermal equilibrium. If two objects with different temperatures are brought in contact, heat energy will flow between them, and after some time their temperatures will even out. Of course, we need to also imagine that the objects do not interact with the surroundings around them, so heat does not leave the system of two objects. It can only flow between those two objects. So when the temperatures of those two objects even out, the flow of energy or heat energy stops, and then we say that the two objects have achieved thermal equilibrium. So imagine that we have this metal cube made from, let's say, steel, and it's at high temperature, so it's hot. Now let's take another cube made of steel that is at low temperature, and we say that this is cold. Let's bring those two in contact with each other. Bringing the two cubes in contact with each other and isolating them from the surroundings will result in heat energy flowing from the hotter cube towards the colder cube. So the molecules, or atoms rather, of the steel in cube A will lose energy, and the atoms of cube B will gain energy. This process will continue until the two cubes have the same temperature. So as cube A loses energy, its temperature drops. As cube B gains energy, its temperature rises. And this process will stop when the two temperatures are equal. Once the two temperatures are equal, the temperature of cube A equals the temperature of cube B. There is no more transfer of heat energy between the two cubes. And then we say that those two cubes have achieved thermal equilibrium. So any two objects that are at the same temperature essentially are in thermal equilibrium. They don't even have to be in contact with each other. As long as their temperatures are the same, they are in thermal equilibrium. This statement is at the heart of the Zeroth Law of thermodynamics. Let's illustrate the point. So here is the example. We have a cube A made from a random type of material, brought in thermal contact with an object C, a cylinder C, made from random type of material. But we see that there is no heat flow between the two. That means, from the previous consideration or discussion, that A and C are in thermal equilibrium. They are at the same temperature. Then I'm going to bring object C in contact with a different block, B. It can be made from different material than A. It can be the same material. It doesn't matter. And then we again see that there is no heat flow between C and B, which then means that C and B are in thermal equilibrium. They are at the same temperature. Then, what happens if I bring A and B into contact? The expectation would be that there will be no heat flow, and if such experiment is conducted, that will be the result. When A and B are brought in contact, there is no heat flow. Then that means that A and B are in thermal equilibrium as well. And this is the essence of the Zeroth Law of thermodynamics. Now let's state the Zeroth Law a little bit more coherently in a single sentence. The Zeroth Law of thermodynamics states that if objects A and B are in thermal equilibrium with a third object C, then A and B are in thermal equilibrium with each other. On the previous slide, when I showed you the example of the setup, the object C this could be a thermometer. So object C is a thermometer. And so we know that if two different objects have the same temperature, then they are at the same temperature. They are at thermal equilibrium, and based on the Zeroth Law of thermodynamics, it means that if we bring them in contact with each other, there will be no heat flow between the two objects. The first law of thermodynamics is about the relationship between the internal energy of a system, for example, gas. Remember, the internal energy was the energy that the molecules of the system or the atoms contain or have. This internal energy was made from, or was the sum of, the kinetic energies of translation, rotation, vibrational kinetic energies, possibly potential energies of interaction between the molecules or atoms of the system, and then there can be others as well. So the internal energy of a system, then also the relationship that the internal energy has to the amount of heat gained or lost by the system, and the relationship that internal energy has with the work done on or by the system. So to illustrate the meaning of those statements, let's look at the system as a system of molecules, or in other words, gas, that is contained in a cylindrical container with a movable piston on one side. Here is my container. One side is fixed, the other side is blocked by a piston that can move to the left or to the right, and the gas inside this cylinder is those orange dots, so those are the molecules. So left on its own, these molecules will be moving in all kinds of random fashion, and the gas or the system will have a certain amount of internal energy. Now, if I place a heat source right here at the lower left corner of the container, that will result in adding heat to the system. So as a result of the heat added to the system, these molecules here will start to move faster in all directions, and that means that the pressure of the gas inside will increase. Well, the pressure then increasing means that more force will be applied to this moving piston, and so the piston is going to move to the right. But this is the same as doing mechanical work, because these molecules apply some force on the piston moves certain distance to the right. And so then the internal energy here that the gas will have is equal to the amount of heat that was added to the gas plus the work that the gas did on the piston. Another possibility is the heat is removed from the gas. Imagine we dip this cylinder in a bath of ice, and then on top of that the piston pushes in to the left. That will result also in change of the internal energy of the gas. The molecules will be moving slower because heat is being removed from the system, and then work is being done on the system. And so the relationship between the internal energy of the system, the amount of heat that's gained or lost by the system, and the work done on or by the system is the following. The internal energy of the system is equal to the heat gained or lost by the system plus the work done on or by the system. So this is the statement of the first law of thermodynamics. This essentially is an equation of conservation of energy. So energy flows in or out of the system, work is being done or by the system. As a result, the internal energy of the system changes. Before we talk about the third law of thermodynamics, we must discuss the concept of absolute zero. the temperature of a system can be lowered by removing heat from it, which will decrease its internal energy. Once all the internal energy is removed, so enough heat is taken away from the system so that the internal energy essentially becomes zero, the lowest possible temperature of this system is reached. This temperature is known as the absolute zero. In other words, a system with zero internal energy is at temperature known as the absolute zero temperature. The absolute zero temperature is measured on the absolute temperature scale. The absolute temperature scale is also known as Kelvin scale. On that scale, 0 Kelvin is equal to negative 273 degrees Celsius. And conversion from Celsius to Kelvin happens by adding 273 to the temperature in Celsius degrees. Now we are ready to make a statement of the third law of thermodynamics. The third law of thermodynamics states that absolute zero can be approached experimentally but can never be achieved. According to my research right now, the lowest achieved temperature in a lab is 1/billionth of a Kelvin. So that means that this is 0.000000001 degrees Kelvin. So the statement of the third law states that this can never become a zero. Just people can add more zeros in front of the one, but it will never become zero. It's impossible to achieve. And the reason for that would be that there is always some transfer of heat from the surroundings into the experiment, so it's impossible to completely eliminate that. Now let's discuss heat capacity. Heat capacity Q is the amount of heat needed to increase or decrease the temperature of an object by a certain amount. The heat capacity Q is equal to this coefficient C, which is known as specific heat, times the mass of the object, times the change in temperature that we are looking for. Now, as you can see, the amount of heat that is necessary for the same change in temperature will depend on the mass of the object. That means that if you have two objects made from the same material, one is twice as massive as the other, the heavier object will require twice as more heat for the same change in temperature. This means that the heat capacity is a property that depends on mass. Can I come up with a different quantity that is actually independent on mass? No matter what the mass of the object is, that quantity remains constant for the same change in temperature. Yes, I can, and that quantity is specific heat. And so the specific heat C is the amount of heat needed to increase the temperature of 1 gram of substance by 1 degree Celsius. Specific heat can be expressed from the formula of heat capacity. The specific heat is equal to the heat capacity Q divided by the mass of the substance divided by the change in temperature. As I explained before, if the mass increases, that will also increase the heat capacity. However, if the mass doubles, the heat capacity will double. If the mass triples, the heat capacity will triple, and so on and so forth. So in the end, the ratio here remains the same. And so the specific heat is an intrinsic parameter that can be used to identify different substances because the different substances have different specific heats. The other meaning of specific heat is the value of the specific heat for each material. The higher the value, the more heat it takes to change the temperature by a certain amount. For example, if you place an empty pot of steel, made of steel, on a hot stove top, it's going to heat up from room temperature to, let's say, 100 degrees Celsius very quickly. Now take a pot that is made from, imagine the pot is made from water and it has the exact same mass as the metal pot. Place it on the hot stove top. You will find out that it takes longer for that pot, imaginary pot made of water, to heat up to the same temperature as the metal pot. That is because the specific heat of water is much higher than the specific heat of steel, which means that it takes a lot more heat to change the temperature of water by the same amount as the temperature of steel, and both have the same mass. And water has one of the highest specific heats of substances that are available for common use. And that's why water is very useful for heating and cooling purposes. The only downside of water is that the temperature range in which it can operate is very limited. Water freezes at 0 degrees Celsius or 32 Fahrenheit and boils at 100 degrees Celsius or 212 Fahrenheit. So, for example, for heating and cooling in cars, instead of water, a mixture of water and polyethylene glycol is used, which is known as antifreeze. And this mixture has much larger range of operation than pure water, but it still has very high specific heat. And it's very good medium for heating and cooling of the vehicle. To illustrate the concept of specific heat, let's do the following example. If 11 calories of heat are required to raise the temperature of an 8-gram copper coin by 15 degrees Celsius, what is the specific heat of copper? So let's see what we know. We know the amount of heat necessary for the temperature change, that's 11 calories. The mass of the coin is 8 grams, and the change in temperature is 15 degrees Celsius. What we're looking for is the specific heat. So the specific heat is calculated as Q divided by M times delta T. And so let's substitute and see what we get. We get that the specific heat of copper is 11 calories divided by 8 grams times 15 degrees Celsius, or this is 0.092 calories per gram degree Celsius. So the units for specific heat can be calories per gram per degree Celsius, or kilocalories per kilogram per degree Celsius, or joules per kilogram per Kelvin. It just depends on how the problem is stated. And so with this, I conclude the lecture on thermal energy.